Good afternoon, everyone. I'm a PhD student. My name is Wang from University of Colorado, Denver, and my topic is the interface between CFRP sheets and concrete exposed to freeze-thaw cycles. I will follow these contents to start my presentation: introduction, experimental results, agent-based modeling on moisture diffusion, summary, and conclusions. CFRP composite are often employed as a strengthening material for decrepit concrete structures. To improve flexural behavior, CFRP sheets may be bonded to the tensile surface of the member using the epoxy. Insufficient design guidelines are available on the effects of variable bond lengths for CFRP strengthened concrete members. Additionally, existing research shows inconclusive results about the behavior of CFRP concrete interface under the freeze-thaw exposure. Also, we propose an agent-based modeling to simulate a moisture diffusion using the NetLogo software, while it is still ongoing. For the specimen details, the concrete blocks with 300 mm long times 50 mm wide times 100 mm deep were prepared. Each specimen has a notch at midspan with 50 mm deep, following ACI specification. CFRP sheets were cut with variable bond lengths with 45 mm, 67.5 mm, and 90 mm for 0.5 effective bond lengths, 0.75 effective bond lengths, and 1.0 effective bond lengths. And this is the equation to calculate effective bond length, which is related to the Young's modulus of CFRP, the thickness of CFRP sheets, and compressive stress of concrete. All of the specimens were conditioned in freeze-thaw chamber for 300 cycles, which are approximately 1200 hours. The temperature range was set up from 15 Celsius to -10 Celsius. This slide shows the real-time strain response up to 300 freeze-thaw cycles. So the first picture shows the temperature variation. The second picture, the third picture, and the fourth picture shows the strain variation of concrete, CFRP, transition zone between concrete and CFRP. And from the figures, we can see the strain variation of concrete shows a wider range compared with CFRP, because the coefficient of thermal expansion of concrete is higher than the coefficient of thermal expansion of CFRP. And the strain variation of transition zone between concrete and CFRP was stationed in between these two. Let's take a look at the load displacement response of specimens with variable CFRP bond length. So this picture shows the instrumentation, and we have the load cell to record the load, and have the linear potentiometer to record the displacement and midspan, and use the displacement traducer, where we see the package to record the notch opening displacement. We have a clamp to clamp on one side of concrete specimens and leave all the other side with unclamped condition. Compare these two pictures. A trend of linear response can be observed for all the cases, while the stiffness was affected by bond length. So we can see no matter before and after freeze-thaw cycles, the specimens with 1.0 effective length has the highest stiffness, and the specimens with 0.5 effective bond length has the lowest stiffness. So we can see stiffness was a function of bond length. And for the damage index was defined as 1 minus stiffness ratio, and KFT and K0 means stiffness of specimens with and without freeze-thaw cycles. So we can see the damage index, it decreased with the increase in bond length. That means the gap of stiffness of specimens with and without freeze-thaw exposure went up. Let's move forward to the notch opening of specimens with variable CFRP bond length. As discussed before, we use displacement transducer OOC package to record the notch opening displacement. Compared with these two pictures, we just take the unconditioned specimen with 1.0 effective bond length as an example. So at the very beginning, the response was linear up until 6 kN, and after 6 kN, the displacement suffering owing to the initiation of macrocracks can be noticed. So after 12 kilonewton, given that apparent reduction in the load displacement response, and we may see the notch opening may be more susceptible to the crack formation. And the specimens with 0.5 effective bond length and 0.75 effective bond length demonstrate the similar response. After 300 Freeze-Thaw cycles, no matter which specimens, a significant decrease about the slope is much more obvious and it reduced greatly. Digital image correlation, OEC-DIC, is used a pixel movement to calculate the strain and displacement contour of the required area. It took pictures from a monochrome camera and record the pictures with the interval of 1 second. So we can get the pixel movement of horizontal displacement to describe the crack propagation. And also we have the load cell to record the load, so we can know the relationship between the increased load and the crack propagation. So for example, the crack was initiated at around 70% of peak load. And after that, the crack was propagated until the peak load, and then the failure would happen. Let's take a look at the failure modes. The failure modes was not affected by Freeze-Thaw, but it was a function of bond length. Because we have a clamp on one side of specimen, so all the failure was observed on the unclamped side with variable bond length. For the specimens of 0.5 effective bond length, the stress concentration at the CFRP termination initiate a crack and propagate towards the notch tip with the angle of 45 degrees. This kind of failure diminished with the increase in bond length because mid-span notch control the failure before the progression of crack. And for the energy release of crack propagation, the energy was overturned from the load displacement response up to the failure. In principle, a crack propagates when the energy release rate of the specimen is greater than the rate of crack formation. And also the crack propagation we detected from previous DIC techniques. So we can correlate between energy and the crack propagation. So for the specimen of 1.0 effective bond length, we can see the energy is higher than all the other two cases. But the trend of 1.0 effective bond length and 0.75 effective bond length is similar. And after Freeze-Thaw cycles, we can see the energy was decreased due to the deterioration, while the trend between energy and the crack propagation was well maintained. And for the fundamental frequency test, the frequency was also decreased due to the increased Freeze-Thaw cycles because of a deterioration. Also, the specimen with 1.0 effective bond length has a higher frequency than the other two cases because it is related to the stiffness. The longer CFRP bond length can improve the stiffness of a specimen and make the specimen stronger. And for the mice test, the mice was also decreased with increased Freeze-Thaw cycles because of concrete deterioration. From these pictures, we can see within 300 Freeze-Thaw cycles, the cement was disappeared at the top surface and aggregate was exposed to the air. Sometimes the concrete spalling would also occur. Let's move forward to the concrete surface and the CFRP deterioration at 20 times magnification using the macroscopic images. We compare the pictures of 0 cycles, 100 Freeze-Thaw cycles, and 300 Freeze-Thaw cycles. You can see the cement was disappeared gradually, and the aggregate was exposed to the air. And this picture shows a more severe condition. Also, the epoxy resin was discolored with the increased Freeze-Thaw cycles. Let's take a look at the macro cracks near the notch tip at different times magnification using the macroscopic. Also compare these 3 different cycles at the beginning and nothing happened here. And at 100 cycles close to the tip, the aggregate was exposed sometimes. For the 300 cycles, we can see the micro cracks was occurred close to notch deep. And when zoom in this picture and use the 20 times magnification, 50 times magnification, and 100 times magnification use the microscopic, and we can see the micro crack close to notch deep is pretty clear. Let's take a look at the interface between concrete and CFRP at 20 times magnification. Also compare the different cycles. At the very beginning, we can see the interface between concrete and CFRP are pretty good. And for 100 freeze-thaw cycles, some micro cracks was initiated at a notch along the CFRP sheets and at a CFRP termination. We compared as with 300 freeze-thaw cycle, we can see this kind of a micro crack was expanded. No matter at notch, along CFRP sheet and at CFRP termination, this micro cracks was pretty clear, compared with all the other two cases. Let's move forward to the theoretical support. And we try to use agent-based modeling, use a NetLogo software to simulate the moisture diffusion. We use the finite difference method to calculate the concentration of all the points in the specimen. Also, we looked into the diffusion coefficient of different material from the lateral view temporarily, such as epoxy, CFRP, and concrete. We can see the diffusion coefficient of epoxy is lower than the CFRP and lower than the concrete. That means that epoxy has the highest resistance with freeze-thaw with moisture diffusion. So it can when CFRP bonded with concrete with epoxy, it can protect plain concrete with moisture diffusion. These images is from the NetLogo software, and we simulate the left side as the plain concrete, and the right side with the concrete bonded with CFRP with a thickness of 1 millimeter. So we can see when external moisture comes through, and the epoxy and the CFRP protect the plain concrete with the moisture. But with the time increase, we can see the moisture penetrated into the concrete, and it increased with the time went up. Also, from the software, we can get the relationship between the concentration and the diffusion distance at a specified time. And we also can get the relationship between the concentration and the time at the specified depth of the specimen. Let's take a look at the summary and the conclusions. Because of different coefficient of thermal expansion, the real-time concrete strength during freeze-thaw cycles was higher than the CFRP strength. The strength of a transition zone was stayed in between these of the concrete and the CFRP. The local displacement behavior of specimens were generally linear up to failure. The notch opening displacement of specimens demonstrate the displacement suffering that was caused by micro cracks at the tip of the notch. The failure node of specimens was not influenced by the freeze-thaw, while it was a function of bond length. Both fundamental frequency and the mass of specimens decreased with increased freeze-thaw cycles. Epoxy resin was discolored. Concrete surface would deteriorate. Local debonding accompanied by micro cracks occurred when freeze-thaw cycles went up. Also, an agent-based modeling used the NetLogo software was simulated on moisture diffusion. And thanks to technical support from Dr. Kim, and Jun Wang is also a PhD student from our school, and thanks for her modeling part. And thank you for your listening, and let me know if you have any questions.
May I come back to your last conclusion, please? So first of all, I would like to congratulate to your research. This is very important and indicated rather considerable deterioration. Well, I remember to the conclusion. So you indicated the influence of the bond lengths of the strengthening material. So my question is directed to practical applications and understanding of your results in practical cases. I understand that in this case you did not have reinforcement inside, and you have a given length of different lengths of the different bond lengths. So my question is to give your impression, not a direct answer, just very easy, just your impression. So in practical cases, just consider a bridge. You have normally strengthening materials from one end to the other end of the beam. Let's take this example. In addition to that, we have internal reinforcement. So how these altogether may influence your results? I'm sure that both of them have influence. Thank you.
Thanks for your questions. I think your question is whether it's influenced if the concrete has some reinforcement inside, right? So now this is just for the material characterization. So only for the plain concrete and the plain concrete bonded with CFRP or with improved with CFRP. And the next step, I think, but because it's only for the small scale specimens, it's not the always see the maybe large building or bridge in the real world. So maybe the next step will include the reinforcement and see whether it has difference between the concrete with reinforcements inside or the plain concrete.
Yeah, I was wondering, thank you for your interesting presentation, if you could give us more detail about the hypothesis about diffusion you've taken. Is it a linear diffusion? The softer, you goes very quickly. What's the boundary conditions?
Okay, I will go back to maybe.
That's it.
Yes. So actually, at this stage is the theoretical, because you can see it is still ongoing. At this stage, we just use a finite different method as the equation showed in the screen, and to calculate the concentration of points in all the points of the specimens. So actually, it's not a linear.
Okay.
So based on this equation, because it can depend, we can calculate all the points with the increased time, or we can get the diffusion at the specific depths.
Okay.
Such as 1 millimeter, 2 millimeter, and it depends. So the calculation without this finite different method, so it's not linear. Actually, the trend maybe with the time is with the diffusion distance is non-linear.
And on the next slide,
okay.
It seems that the diffusion is only on one way, and maybe it can go under the.
Yes, it is the first stage, or we see the ideal condition. All of the moisture or water is come from the total surface. But after that, or next step, or in the future work, we will assume the water or the moisture comes through all the other directions
to get
combine.
to the diffusion.
Yes, because in the experimental result, it's in the experimental work, we put the specimen in the freeze-thaw chamber. So water is come from all of the directions. So this is just the ideal condition for one direction at this stage. Thank you for your question.